So in this problem, I'm just sort of assuming that these two sets D and F are vector spaces, and we could go through like that big long definition of what a vector space is and go through them all, but for the purposes of the problem, just trust me that they are. And what I want to show is that this set D is actually a subspace of this set F. And to show a subspace, you don't actually have to show that like the zero vector is in there, but it's good to do that. And you know, you can kind of think like you know, D is the set of differentiable functions. Like just if you take d dx of 0, right, it's 0. And that that function acts as the zero vector in that set, and that zero function is actually also the zero vector in the set F. So you don't really have to do that part because it's not part of the definition for what a subspace is here, but it is good to realize that that vector is in both sets. What we do have to show is basically that if you have so if you take the derivative of a sum of functions in D, okay, then basically it should be the same thing as just taking the derivative of the sum of each individually, right? And we know just by like properties of the derivative, right, if we take the derivative of like the quantity f plus g, it's the same thing as f prime plus g prime. And so that is like really all you have to say for the first property, that the derivative is really what it's doing here is it's working as a linear operator, and you can just apply it to both. And that's part of why it's also a vector space and things like that. And then for the other part, we have to deal with the scalars. So if we have like some scalar c times f prime, right, we know that we can take, when we take a derivative like this, we can pull the constant c out, and then we just have f prime. And really that's what we had to show. Like any thing in D, any arbitrary f and g, and any scalar c that would, come from like the reals. So maybe I should add that. So the field that we're talking about here is like the reals. And they would satisfy this just based on properties of the derivative. And those are the two things you literally have to show that this space is a subspace of F, the set of all real valued functions. That's it. And so there's a problem in the book where it asks you to do this kind of subspace thing that we just did, but for 3 different spaces. And one is just the set of all like vectors, like the way we've been thinking of vectors so far, of the form like AB minus B and A. And, those kind of vectors are in R4, and we want to just show that this arbitrary set of all these vectors is a subspace of R4. The way you do that problem looks the same as the way you solve this problem, which is showing that the polynomials of order 3, so a plus bx minus bx squared plus ax cubed, is a subspace of P3. And then it's also going to look the same as trying to do the same problem, but for matrices of the form AB minus B and A in this space, the M like 2 by 2, 1. And I'm not going to go through it all, but you should read this example in the book because you're going to see that it feels the same like structure in all different cases, the same way as like this problem felt with the derivative. And that is actually connected to this word that you're going to learn about in a few videos. And I was talking about this during the time of Game of Thrones before, when the season 3, or sorry, not 3, what was it, 7 finale was going on. And so that was my joke from before. And now it doesn't apply, but it's still there. And so you should read this, because what you're going to notice is that all three of these problems feel exactly the same way as also this problem over here. And the fact that they all kind of are the same sort of problem is actually connected to a very important concept that gives us the power to basically say that these three subspaces are really the same kind of subspace. Like, it doesn't actually matter if we talk about it with polynomials, or if we talk about it with matrices, or if we just talk about it with like vectors with 4 components. To me, they literally are all the same thing. And that's like a really powerful result in linear algebra when you get to the point where you can mathematically show that that really is the case. But you should read through all those because you'll notice the similarities between all three. All right, one last thing that I want to talk about here is that span carries over like really nicely from like all the stuff we did in Rn to any abstract vector space that we want to talk about. So we can talk about like span of polynomials, which is totally okay to do. So if we wanted to figure out, so this is some polynomial in P2, right? And the question is it in the span of these two polynomials? So the way I think about this problem is basically it's like a 3D problem. And, P of x might be, this vector right here. And then Q of x might be this vector. And so the plane that is spanned by them, the question is R of x here in that like plane right there, okay? And try to visualize that in 3D. I know it's a pretty bad picture. But that is basically what we've sort of worked with, with these columns of numbers. That's kind of how we've thought of it. But you can actually think about that like geometric idea, but you can actually put the context of polynomials in place of the numbers that you're used to, okay? So, like more concretely, basically what we're doing is we're saying is some amount C of P of x, which actually let's put in what it is here. So it's 1 minus x, oh wait, wrong color. 1 minus x plus x squared is like C times that plus D times Q, which is 2 plus x minus 3x squared, equal to R of x, okay? So basically, is there some linear combination, right, of these polynomials that get you to R? So at this point, you can literally just go and like distribute C and D in. And if you do that and then like group all your terms, you'll have C plus 2D for like the constants, and then minus C plus D times x, and then plus C minus 3D times x squared. And then R of x is just my 1 minus 4x plus 6x squared. And so what you get now is a way to like, you can start bringing in linear algebra because you can get a matrix out of this. So if you look at what, if we just look at both sides, we need to equate C plus 2D needs to equal 1, right? So that's going to give me one equation that relates C and D. Then, let's see, I can't pick a color. How about that color? Minus C plus D has to equal minus 4. So we have minus C plus D minus 4. And then last but not least, we would have like C minus 3D equals 6, right? C minus 3D equals 6. And then, we've done this kind of thing already before. Now we can, we have a system of 3 linear equations, and we can make a matrix out of it and solve that matrix, literally. So we have like 1, negative 1, 1, 2, 1, negative 3, 1, negative 4, 6. And like now, we've just turned this problem into like an Rn world that we're kind of used to working with. And the way I think about it now is like, it's just we're augmenting these vectors with this one, and we're basically saying, is there a combination of 1, negative 1, 1, which you can kind of see back here, 1, negative 1, 1, and 2, 1, negative 3, 2, 1, negative 3, to get this would be like your R of x, your 1, negative 4, 6. And then, so now you just literally do like RREF stuff, and you get this. And then from that, you can see, right, that like C equals 3 and D equals negative 1. And I'm not going to go through it all because it takes kind of a bit of time, but literally if you take this, right, and you just plug in those C and D's up here, I guarantee you, if you then distribute C and D, you will get R of x. So, so this notion of span, like, which we started off first just thinking about like arrows and, you know, building up, like in this case, it was, if you're looking at 2 arrows in space, the span would be the plane, right? Like that I kind of drew here. Now we can abstract that to saying, think of, you know, what one polynomial P of x like maps out. What does that quadratic look like? And then what does this quadratic look like, right? They're definitely different quadratics. And from some linear combination of those quadratics, we can get another quadratic. And this leads into like all sorts of cool stuff in, we do some like differential equations where we basically do these sums of sines and cosines, these like linear combinations of sines and cosines, and that's something called like a Fourier series, and it's super useful in like pulling out important properties of like what they call the phase space of certain differential equations, and then it's easier to solve them in the different phase spaces, and then you can like switch back, and there's all sorts of stuff there to say, but the concept is built out of this concept right here, where we're just taking linear combinations of functions to get other functions. That's what all span of this vector space would be.